Hi, welcome to our video introduction on 2x2 systems of equations. And we're going to use the transformations of the coordinate plane that you get from matrix multiplication that we talked about in the last section to solve 2x2 systems of equations. Now, in Algebra 1, you learn about solving systems of equations where we have two or more equations at once that we need to solve for. So here we have two equations, 2x minus y equals 4 and x plus y equals 5, and we have two unknown variables. We have an x variable and we have a y variable. And the solution to this system of equations is the point for x and y, the coordinates of x and y, that make both equations true at the same time. So one method which you usually start solving systems of equations in Algebra 1 with is to graph the left-hand side, or excuse me, the first equation, which in this case is 2x minus y equals 4, that's this line in red, and then graph the second equation as well, the x plus y equals 5, and find the point of intersection, which in this case the intersection point is at 3, 2. And if we plug 3 and 2 in for x and y, it'll make both equations true. So 3 plus 2 does give us 5. 2 times 3 is 6. 6 minus 2 does give us 4. So we can see by graphing each row, we can find where they intersect, and that's the solution to our system. We also have special cases where we get no solution, there's no intersection points, and that'll happen when the lines are parallel. So here we have x plus y equals 2 in red and 2x plus 2y equals 1 in blue. They have the same slope of -1, and they're starting with different y-intercepts. So these two lines are never going to intersect, which means there's no solution to this system of equations. There's no value of x and y you can plug in to make both equations true. For instance, if you tried 1 plus 1, that does give you 2, but 2 times 1 plus 2 times 1 does not give you 1. So if we have parallel lines through graphing the rows, we have no solutions. Or we can have an infinite number of solutions where we are actually graphing the same line twice. So for instance, we have 2x minus y equals 1, and then 4x minus 2y equals 2. So if we graph one, let's say we graph the first one here in red, and then we graph the second one in blue, well, if the blue line lies on top of the red line, here I just indicated that with purple since red and blue make purple, at least according to my elementary school art teacher, then we get the same line twice, which if it's the same line, one line on top of the other, we actually have an infinite number of intersections. So any point that makes the first equation true will automatically make the second equation true. For instance, we have the point 0, -1. So 2 times 0 minus -1 does give us 1. 4 times 0 minus 2 times -1 also gives us 2. So any point that works on the first line automatically works on the second. What we're going to look at, though, is a matrix interpretation for systems of equations. And this will help out when we get into just, instead of 2x2, maybe 3x3 or even more than that. And that's also how computers how they solve systems of equations through matrices. They don't graph them and try to find intersection points if they exist. But in the previous section, we looked at matrix multiplication. So if we write this system of equations that we're looking at in matrix form, we get 2, 1 for our first column and -1, 1 for our second column. And then if we multiply that by x and y, we'd have x times this first column, so x times 2 and x times 1, x times 2, x times 1. And then we'd have y times this second column, y times -1, y times 1, y times -1, y times 1. And it equals this vector column here of 4, 5. So 4, 5. So our matrix form for our systems of equations looks like this. And if we expand it out a bit, we get x times the first column plus y times the second equals the column 4, 5. So notice that with our matrix here, I hat gets sent to 2, 1, and j hat gets sent to -1, 1. And we're multiplying x by where I hat's going to go. We're multiplying y by where j hat's going to go. So if we multiply by that matrix, we get this brand new coordinate system that I have here in the purple dash grid laid on top of our original coordinate system. So notice I hat gets sent to the vector 2, 1. So go over 2, up 1. This is our new I hat. So this is going to represent in this purple coordinate system 1 on the x-axis, this point right here. And this would be 2 on the x-axis, 3 on the x-axis. Here's -1 on the x-axis, -2 on the x-axis. For j hat, it gets sent to the point -1, 1. So -1, 1. Here's our j hat. This is going to represent 1 on our new y-axis for this purple dashed grid. So here's 1 on the new y-axis, 2 on the new y-axis, 3 on the new y-axis, -1 on the new y-axis, -2 on the new y-axis, etc. And so if we look at that point that was on the other side, 4, 5, if we were to plot that point in our original coordinate system, the gray coordinate system in this case, what it ends up looking like is something like this. And the idea behind systems of equations with matrices is under this new coordinate system for I hat and j hat, what are the coordinates of this point here that was originally over 4 and up 5, but now in I hat and j hat, this new purple coordinate system, it's actually going 1, 2, 3 I hats and 1, 2 j hats. So in our new coordinate system, we actually have our solution is going to be 3 of these I hats. So 3 of the I hats, and then 1, 2 of the j hats. And notice that point 3, 2, if we go back and look from before, that point is actually the same as the intersection point if we graph the rows of each equation. So the columns create this new coordinate system using matrix transformations, and now given this point in the original coordinate plane, how can we get there using combinations of I hat and j hat? In this case, we need 1, 2, 3 I hats followed by 1, 2 j hats. So that's what we're going to look at today. Now, it's important to note that for our special cases, our no solution or our infinite number of solutions, our transform coordinate system is going to become a single straight line. So for instance, if we look at x plus y equals 2 and 2x plus 2y equals 1, we said that one had no solution. Those lines were parallel. If we look at them in terms of vectors, we have the vector 1, 2, so over 1, up 2, here's I hat. We also have j hat at 1, 2. So I hat and j hat are parallel. They're scalar multiples of each other. In this case, scalar multiple of 1. So if we graph that new coordinate system, it just becomes a line. And notice this point, the point 2, 1, is no longer, it's not on this line. So if this point is not on this purple line, we can never, no matter what we do, if we're only traveling along this purple line, we can never get to this point. So there's no possible way we can get there. There's no solution to this system of equations. Likewise, we have, for this one, we have the I hat gets sent to 2, 4, so over 2, up 4. J hat gets sent to -1, -2, so -1, -2. The vectors 2, 4, and -1, -2 are also scalar multiples of each other. So we get a single line once again. And this time, if we look at the point 1, 2, 1, 2, this point is on this line. So maybe we can, instead of going 1 for j hat, we can go -1 for j hat. Or maybe we can go 1 for I hat and then subtract 1 for j hats. We actually have an infinite number of ways we can get to this point if that point happens to fall on that line. So, all right, that about does it for this video. We'll look at some more examples in how to use GeoGebra, an app that I don't want to say it's an app, but it's a matrix transformations with systems in GeoGebra for a few of our examples. So